In this video we're going to see how to use integration to find the centre of mass of objects which are solids of revolution. In the previous video we saw how integration can be used to find the centre of mass of a wide variety of two-dimensional shapes, and we're now going to move on to find the centre of mass of 3D shapes that can be viewed as solids of revolution. So let's start with the line segment y equals r divided by h all times by x for values of x between 0 and h, and then consider the triangular lamina that's formed by this segment and the line x equals h and the x-axis. If we now rotate this lamina by 360 degrees about the x-axis, then we're going to obtain a shape like that, which is of course a cone of radius r and height h. Now it's worth noticing that for this cone that we've got here, the y equals 0 plane and the z equals 0 plane are certainly going to be planes of symmetry for this three-dimensional cone. So we've got the y coordinate of the centre of mass must equal 0 and the z coordinate of the centre of mass must equal 0. So that means that the only thing we've got to calculate is what the x coordinate of the centre of the mass is. Now to do this, what we're going to do is we're going to consider a small strip of the triangular lamina which is parallel to the y-axis and has width delta x. We're going to let the point x0 be at the bottom left-hand corner of this strip and the point xy be the top left-hand corner of this particular strip. If we now rotate this strip by 360 degrees about the x-axis, we're going to obtain a thin disc or cylinder whose radius is going to be y and the depth or height of this particular cylinder is going to be delta x. So the volume of this disc is going to be pi y squared delta x. If the density of the cone is rho kilograms per meter cubed, then for this small disc the mass is going to be rho times pi times y squared times delta x, and the coordinate of the centre of mass, or the x coordinate of the centre of mass for this small little disc, is going to be approximately equal to x. So the sum of the mx's for this disc is going to be approximately rho pi times x times y squared times pi delta x. And the smaller the value of delta x is, the better these approximations will be. So there are the results we had from the previous slide. For the whole cone, the mass then can be approximated by taking the sum between x equals 0 and h of all of these rho pi y squared delta x's. The smaller the value of the delta x's, the more accurate the approximation will be. So we can say that m is the limit as delta x tends to 0 of the sum between x equals 0 and h of rho pi y squared delta x. And as we've seen before, a limit of a sum like this can be rewritten as being an integral, and provided rho is constant throughout the material of the cone, then we've got the rho and the pi can be pulled outside of the integral sign, so we can say that the mass is equal to rho times pi times the integral between 0 and h of x squared. Which means that we can write that the mass is rho pi times by the integral of r over h times x all squared. So that is r squared over h squared times by x squared has got to be integrated, which gives me r squared over h squared times by a third x cubed. I've got limits of h and 0, so that gives me rho pi times r squared over h squared times by a third h cubed minus nothing. In other words, I'm ending up with 1/3 rho times pi times r squared over h squared times by h cubed, which just cancels down to 1/3 rho pi r squared h. Moreover, the sum of the mx's for the cone is going to be approximated by the sum between the x equals 0 and x equals h of the rho pi xy squared delta x's, which was the sum of the mx for one little disk. The smaller the value of delta x's, the better that sum is going to be as an approximation to the sum of the mx's for the cone. So we can say that the sum of the mx's for the cone is the limit as delta x tends to 0 of the sum between x equals 0 and h of rho pi xy squared delta x, which becomes rho pi times by the integral between 0 and h of xy squared. We know that y is r over h times by x. So we've got the sum of the mx's for the cone is equal to rho pi times by the integral between 0 and h of x times by r over h times x all squared. And if we work that out, we end up with 1/4 rho pi r squared h squared. So the x-coordinate of the centre of mass for the cone is the sum of the mx's for the cone divided by the mass of the cone, which is 1/4 rho pi r squared h squared divided by 1/3 rho pi r squared h. And that cancels down to 3/4 h. So we have shown that the centre of mass of the cone is 3/4 h away from the vertex or the top of the cone, or equally 1/4 h away from the base of the cone. Now the argument that we've had for the cone can be generalized for any object which is a solid of revolution. So the centre of mass of a uniform solid obtained by rotating the curve y equals f of x between x equals a and x equals b completely around the x-axis is given by the centre of the x-coordinate of the centre of mass is the integral between a and b of xy squared divided by the integral between a and b of y squared. The y-coordinate of the centre of mass is 0 and the z-coordinate of the centre of mass is 0. And a very similar argument gives you the centre of mass of a uniform solid which is obtained by rotating a curve x equals g of y for values of y between c and d completely about the y-axis, satisfies the x-coordinate and the z-coordinate of the centre of mass are 0. The y-coordinate of the centre of mass is the integral between c and d of x squared y, integrated with respect to y, divided by the integral between c and d of x squared integrated with respect to y. By and large, I would suggest that you try and remember the first of these two results and always arrange it so that your objects are obtained by rotating a curve around the x-axis. So let's see an example now. So we've got to prove that the centre of mass of a uniform solid hemisphere of radius r is distance 3r divided by h from the centre of the plane of the hemisphere. So, if we start off with a quarter circle in the positive quadrant, if we rotate that positive quadrant fully around the x-axis, then we're going to obtain a hemisphere of radius r. Now, for a solid of revolution produced by rotating the curve around the x-axis, we know the centre of mass is given by an x-coordinate, which is the integral of xy squared over the integral of y squared. The y-coordinate of the centre of mass is 0, and the z-coordinate of the centre of mass is 0. So we've got two integrals to work out. First one is the integral of y squared, and our limits in this case, well, the curve that we've got is y squared equals r squared minus x squared, or y equals the square root of r squared minus x squared, for values of x between 0 and r. So the limits are 0 and r, and we've got y squared is r squared minus x squared, which is a nice easy integral. We get r squared times x minus a third x cubed with values of 0 and r, and that gives me 2/3 r cubed. I substitute r in and then substitute the value when I get substitute x equals 0 in. The integral between a and b of xy squared dx becomes the integral between 0 and r of x times by r squared minus x squared, and that is going to integrate through to give me a half r squared x squared minus a quarter x to the power 4, and when I substitute in x equals r, I'm going to get a half r to the 4 minus a quarter r to the 4, so that gives me a quarter r to the 4. When I substitute x equals 0 in, I get nothing at all, so the value of that integral is a quarter r to the 4. So I can now say that the x-coordinate of the centre of mass is going to be a quarter r to the 4 divided by 2/3 r cubed, which simplifies down to 3/8 r as required. And now part B, a wooden mushroom contains of a cylinder A of radius A and height 12a, surmounted by a hemisphere of radius 5a. The centre of the top of the cylinder is the same point as the centre of the hemisphere. Find the height of the mushroom's centre of mass above the centre of the cylinder's base. Be a good idea to start with a picture of the mushroom. Looking at the picture then, we can quickly see that the planes x equals 0 and the plane y equals 0 are planes of symmetry for the mushroom. So the only coordinate that we're really interested in is going to be the z-coordinate. If we let the density of the wood be rho, then we can go through our normal sort of table of results to try and find out the position of the centre of mass. So if we start off thinking about the cylinder first, then the cylinder has got a radius of A and a height of 12A, so its volume is pi times A squared times 12A, so its mass is going to be pi times A times 12A times by rho, in other words 12 pi A cubed rho. The centre of the mass of the cylinder is obviously halfway up the cylinder by symmetry, so we've got Z bar is 6A. So the sum of the mz's for the cylinder is going to be 6A times by 12 pi A cubed rho, which is 72 pi A to the 4 rho. For the hemisphere, I know that the radius of the hemisphere is 5A, so the volume of the hemisphere is going to be 2/3 times by pi times by 5A cubed, and to get the mass I've got to multiply that through by rho, and that gives me 500 pi A cubed rho divided by 6. Now, previous part of the question, I showed that the centre of mass of a solid hemisphere is distance 3r over 8 away from the centre of the plane face of the hemisphere. So in this case, we've got the centre of mass of the hemisphere is going to have a z value, which is 12A plus 3/8 of 5A, which is 111 over 8A. So the sum of the mz's is going to be 500 pi A cubed rho divided by 6 times by 111 over 8A, which gives me 4,625 over 4 pi A to the 4 rho. So for the whole mushroom, I've got a total mass of 12 pi A cubed rho plus 500 over 6 pi A cubed rho, which is 286 over 3 pi A cubed rho. I've got a sum of the mz's for the whole mushroom is 72 pi A to the 4 rho plus 4,625 over 4 pi A to the 4 rho. So that's 4,913 over 4 pi A to the 4 rho. So Z bar is the sum of the mz's divided by the m, so that's 4,913 over 4 pi A to the 4 rho divided by 286 over 3 pi A cubed rho, which simplifies to a horrendous fraction, 14,739 over 1144A. It's approximately 12.88A. And we've made a modelling assumption that the mushroom is made entirely of wood with constant density. And that concludes our look at integration to find the centre of mass of solids of revolution.